Tonight we're going to talk about something that sounds simple, but is actually one of the most confusing ideas in all of science. Spacetime. You've probably heard this word before. Scientists throw it around constantly. Einstein's theory of spacetime, the fabric of spacetime. Spacetime is curved. But here's what most people don't realize. When you actually dig into what spacetime means, when you try to understand what it really is, you discover something unsettling. We don't know. We use this idea every single day. Your GPS wouldn't work without it. We've photographed it being bent around black holes. We've detected ripples moving through it. And yet, we have no idea what it actually is. By the end of tonight, you're going to understand why this is one of the biggest unsolved mysteries in physics, and why solving it might change everything we know about the universe. Before we dive in, if you're interested in this kind of deep exploration, a quick like or subscribe really helps the channel grow. It makes a huge difference. Now, let's begin. Let's start in 1905. Albert Einstein was 26 years old, working as a patent clerk in Bern, Switzerland. He wasn't a professor, he didn't work at a university. He examined patent applications for electromagnetic devices during the day and thought about physics at night. And in that year, 1905, he published 4 papers that would change physics forever. One explained Brownian motion and proved atoms were real. One explained the photoelectric effect and helped establish quantum mechanics. And 2 papers introduced what we now call special relativity. Special relativity sounds complicated, but the core idea is actually straightforward. Einstein realized that the speed of light is always the same no matter how fast you're moving. This seems impossible at first. If you're on a train moving at 100 km per hour and you throw a ball forward at 20 km per hour, someone standing on the ground sees the ball moving at 120 km per hour. The speeds add up. That makes sense. That's what we expect. But Einstein showed that light doesn't work this way. If you're on a spaceship moving at half the speed of light and you shine a flashlight forward, you might think the light would move at 1.5 times the speed of light from the perspective of someone watching you. But it doesn't. The light moves at exactly the speed of light, about 300,000 kilometers per second, both from your perspective and from the perspective of someone watching you from outside. The same speed always. This seems impossible. How can light be moving at the same speed for both observers when one observer is already moving at half the speed of light? Einstein's answer was radical. Space and time adjust to keep the speed of light constant. If you're moving very fast, time literally runs slower for you from the perspective of someone standing still. And distances in the direction you're moving actually contract. They shrink. These aren't optical illusions. They're real physical effects. Time and space are not absolute. They're relative, depending on your motion. The only thing that's absolute, that's the same for everyone regardless of how they're moving, is the speed of light. This was shocking in 1905. It overturned centuries of assumptions about how the universe works. Newton had built physics on the idea that time flows the same for everyone, that a second is a second no matter where you are or how fast you're moving. Einstein showed that wasn't true. Time is flexible. Space is flexible. They bend and stretch depending on your motion. Think about what this really means. If you could build a spaceship that travels at 99% of the speed of light, and you took a journey to a star 10 light years away and back, from your perspective on the ship, the journey might only take a couple of years. But when you return to Earth, 20 years would have passed. Your friends would be 20 years older. Your children might now be older than you. This isn't science fiction. This is what Einstein's equations predict, and it's been confirmed by experiments countless times. We've tested this with particles in accelerators. Unstable particles that normally decay in microseconds live much longer when they're travelling at 99% of light speed. We've tested it with atomic clocks on airplanes. When you fly an atomic clock around the world and compare it to an identical clock that stayed on the ground, the travelling clock shows less time has passed. The difference is tiny, just a few hundred nanoseconds, but it's measurable and it matches Einstein's predictions exactly. The implications are profound. There's no universal now, no cosmic clock ticking at the same rate everywhere. When you say something is happening right now on a distant planet, that statement has no absolute meaning. Different observers moving at different speeds would disagree about what right now means. They disagree about which events are simultaneous. Time is not a river flowing at a constant rate for everyone. It's more like a fabric that can stretch and compress depending on how you're moving through it. But Einstein wasn't done. Special relativity only dealt with objects moving at constant speeds. It didn't handle acceleration. It didn't handle gravity. And gravity was a problem. Newton's law of gravity had worked brilliantly for over 200 years. You could use it to predict the motion of planets, the trajectory of cannonballs, the orbits of moons. It was one of the most successful theories in the history of science. But Einstein realized it couldn't be right. Not completely. Newton's gravity worked instantly. If the sun suddenly disappeared, Earth would immediately fly off into space. According to Newton's equations, the gravitational pull would vanish instantly across 150 million kilometers of empty space. But Einstein had just shown that nothing can travel faster than light. No signal, no force, no information can cross space instantly. If the sun disappeared, it would take about 8 minutes for the light to stop reaching Earth. That's how long light takes to travel from the sun to us. And Einstein realized gravity couldn't work any faster than light either. There had to be a delay. Something had to carry the gravitational force, and whatever it was couldn't move faster than light. This led Einstein to one of the most productive thoughts of his life. He called it the happiest thought he ever had. It came to him in 1907. He was sitting in his office at the patent office thinking about gravity, when he imagined a worker falling off a roof. While the worker is falling, Einstein realized the worker doesn't feel their own weight. They're weightless. They're in free fall. If they dropped a hammer while falling, the hammer would float next to them falling at the same rate. They wouldn't see the hammer accelerate away or toward them. It would just hover there in midair from their perspective. This seems obvious now. We've all seen footage of astronauts floating in the International Space Station. But Einstein realized something profound. The worker falling off the roof and the astronaut floating in space are experiencing the same thing. They're both in free fall. The astronaut isn't actually floating in zero gravity. They're falling toward Earth just like the worker, but they're also moving sideways fast enough that they keep missing Earth. They're in orbit, continuously falling, but continuously missing the ground. And that's why they feel weightless. Not because there's no gravity, but because they're in free fall. Einstein realized that being in free fall is indistinguishable from being in empty space with no gravity at all. And being in a rocket accelerating upward is indistinguishable from standing on the surface of a planet feeling gravity pull you down. You can't tell the difference. If you're in a closed room with no windows, there's no experiment you can do to determine whether you're standing on Earth feeling gravity or floating in a rocket in space that's accelerating upward at 9.8 meters per second squared. The two situations are physically equivalent. This is called the equivalence principle, and it became the foundation of Einstein's next great theory, general relativity. It took him another 8 years to work out the mathematics, 8 years of struggling with equations, collaborating with mathematicians, making mistakes, starting over. He finally published the complete theory in November 1915, and it was unlike anything physics had seen before. Newton had described gravity as a force, an invisible pull between objects with mass. The sun pulls on Earth, Earth pulls on the moon, you pull on the ground and the ground pulls back on you. It was a force that reached across empty space, and Newton himself admitted he didn't understand how it worked. He said he could describe gravity mathematically, but couldn't explain what caused it. He left that as a mystery. Einstein solved the mystery. He showed that gravity isn't a force at all, it's geometry. It's the shape of space-time itself. Mass doesn't pull on other mass. Mass curves space-time, and objects move along the curves. Imagine a trampoline stretched flat. Now place a bowling ball in the middle. The trampoline surface curves down around the bowling ball. If you roll a marble across the trampoline, it doesn't travel in a straight line anymore. It curves toward the bowling ball, not because the bowling ball is pulling on it, but because the surface itself is curved. The marble is just following the shape of the trampoline. That's how gravity works according to Einstein. The sun curves space-time around it. Earth moves through that curved space-time following what's called a geodesic, which is the straightest possible path through curved space. From our perspective standing on Earth, it feels like the sun is pulling us toward it. But from the perspective of space-time geometry, Earth is just moving in a straight line through curved space. There's no force pulling us. We're in freefall, following the natural shape of space-time. This is a radical idea. It says that what we call gravity, what we experience as a force pulling us down, is actually the curvature of space-time caused by Earth's mass. You're not being pulled down. The ground is accelerating up toward you. Space-time is curved, and you're trying to fall freely through that curved space-time, but the ground keeps getting in your way. That's why you feel weight. That's why you feel pressure on your feet. Not because gravity is pulling you down, but because the ground is constantly accelerating up, preventing you from following your natural freefall path through curved space-time. When you jump off a diving board, you're not falling. You're entering freefall, which is your natural state in curved space-time. You feel weightless for those few seconds in the air because you're finally free to follow the geometry of space-time. Then you hit the water, and the water pushes up on you, stopping your freefall, and you feel weight again. This explains something that had puzzled scientists for centuries. Why does everything fall at the same rate regardless of mass? Galileo supposedly dropped 2 balls of different masses from the Leaning Tower of Pisa and showed they hit the ground at the same time. Newton knew this was true but couldn't really explain why. If gravity is a force pulling on mass, why doesn't a heavier object fall faster? Einstein's answer is elegant. Everything falls at the same rate because nothing is falling. Objects are moving through curved space-time, and the curvature is the same for everything regardless of mass. A feather and a hammer follow the same path through space-time. They move at the same rate because they're both following the geometry. On Earth, air resistance slows the feather, but in a vacuum they fall together. The Apollo 15 astronauts tested this on the Moon. They dropped a hammer and a feather at the same time, and without air resistance, both hit the ground simultaneously. It was a beautiful demonstration of Einstein's theory. Now here's where things get strange. If space-time is curved by mass, and if objects move through that curvature, then space-time must be a thing. It must be something real, something physical. It's not just a mathematical abstraction. It's not just a coordinate system we use to describe where things are. It actually exists. It has structure. It can be bent. It can be stretched. It can ripple like a pond when you throw a stone into it. Einstein's equations describe how mass and energy curve space-time, and how that curvature affects the motion of mass and energy. They're incredibly precise. They've been tested in thousands of experiments and observations, and they've never failed. They predict the orbit of Mercury around the Sun better than Newton's equations. Mercury is close to the Sun, where space-time curvature is strong, and general relativity gets Mercury's orbit exactly right down to tiny wobbles that Newton's theory couldn't explain. The equations predict that light should bend when passing near massive objects. In 1919, during a solar eclipse, astronomers measured the positions of stars near the Sun and found that their light was indeed bent by the Sun's gravity, exactly as Einstein predicted. This observation made Einstein world famous overnight. The equations predict that time runs slower in strong gravitational fields. Clocks at sea level run slightly slower than clocks on mountaintops because sea level is deeper in Earth's gravitational well. The difference is tiny, only about 90 nanoseconds per day, but it's real and measurable. GPS satellites have to account for this. They orbit about 20,000 kilometers above Earth, where space-time curvature is weaker, so their clocks run faster than clocks on the ground. If we didn't correct for this time difference, GPS coordinates would drift by several kilometers per day. The system wouldn't work. Every time you use GPS to navigate, you're relying on Einstein's equations to adjust for the curvature of space-time. The equations predict black holes, regions where space-time curvature becomes so extreme that nothing can escape, not even light. For decades, black holes were considered theoretical curiosities, mathematical possibilities that might not exist in nature. But we found them. We photographed them. The Event Horizon Telescope captured an image of the supermassive black hole at the center of the galaxy M87. You can see the event horizon, the boundary where space-time curvature becomes so strong that light can't escape. Everything about that image matches Einstein's predictions. The equations predict gravitational waves, ripples in space-time caused by accelerating masses. Einstein himself wasn't sure if gravitational waves were real or just mathematical artifacts. For decades, physicists debated whether they could exist. Then, in 2015, the LIGO detectors in Louisiana and Washington state detected gravitational waves from two black holes colliding 1.3 billion light-years away. The signal matched Einstein's predictions perfectly. Since then, LIGO and other detectors have observed dozens of gravitational wave events from colliding black holes and neutron stars. We're now doing astronomy with space-time itself, detecting events by the ripples they create in the fabric of space and time. All of this confirms that space-time is real. It exists, it has properties, it can curve, it can ripple, it can be measured. Einstein's equations describe its behavior with incredible accuracy. And yet, we don't know what it is. We don't know what it's made of. We don't know if it's fundamental or if it emerges from something deeper. Think about what this means. Space-time isn't just a backdrop for events. It's not a stage where physics happens. It's an active participant. It responds to mass and energy. It curves. It moves. It carries waves. In a very real sense, space-time is a physical field, like an electromagnetic field or a gravitational field. But here's the mystery. We know how space-time behaves. Einstein's equations tell us exactly how much it curves in response to mass and energy. They tell us how gravitational waves propagate through it. They tell us how time dilates near massive objects. The mathematics is precise, and the predictions match observations perfectly. But we don't know what space-time actually is. Is it made of something? Does it have fundamental constituents, like atoms are made of protons, neutrons, and electrons? Or is it truly continuous, infinitely divisible, with no smallest unit? Einstein's theory treats space-time as smooth and continuous. You can divide a meter into centimeters, centimeters into millimeters, millimeters into micrometers, and keep dividing forever. There's no smallest distance in Einstein's equations. Space-time is a continuum. But quantum mechanics suggests something different. Quantum mechanics, the other great pillar of modern physics, says that everything comes in discrete units at small enough scales. Energy comes in packets called quanta. Light comes in particles called photons. Even things that seem continuous, like the electromagnetic field, are actually made of discrete particles when you look closely enough. So it's natural to ask whether space-time might also be quantized. Maybe there's a smallest possible distance, a fundamental pixel of space, below which you can't divide any further. Maybe space-time isn't truly continuous. Maybe it's grainy at tiny scales. This is where things get extremely difficult. General relativity and quantum mechanics are both incredibly successful theories. General relativity describes gravity, space-time, black holes, and the large-scale structure of the universe. Quantum mechanics describes atoms, particles, electromagnetic forces, and the behavior of matter at tiny scales. Both theories have been tested extensively. Both make predictions that match observations to extraordinary precision. But they're incompatible. They use different mathematical frameworks. They make different assumptions about the nature of reality. And when you try to combine them, When you try to describe what happens when gravity becomes strong at quantum scales, the equations break down. The classic example is a black hole. A black hole is a region where space-time curvature becomes so extreme that even light can't escape. According to general relativity, at the centre of a black hole is a singularity, a point where density becomes infinite and space-time curvature becomes infinite. The equations predict this, but they also predict that physics breaks down at the singularity. The theory stops working. It gives infinite answers, which in physics usually means you're asking the wrong question or using the wrong tools. Quantum mechanics should become important at tiny scales. When you compress matter into a region smaller than the Planck length, about 10 to the negative 35 meters, quantum effects should dominate. But we don't have a theory that describes quantum gravity. We don't know how to combine Einstein's smooth, continuous spacetime with quantum mechanics' discrete, probabilistic particles. This is one of the biggest unsolved problems in theoretical physics. It's called the problem of quantum gravity. There are several attempts to solve this problem. One of the most famous is string theory. String theory proposes that the fundamental constituents of reality aren't point-like particles, but tiny vibrating strings. Different vibration modes of these strings correspond to different particles. An electron is one vibration pattern. A photon is another. A graviton, the hypothetical particle that carries gravity, is yet another vibration. In string theory, space-time itself might emerge from the collective behaviour of these strings. Space-time might not be fundamental. It might be like temperature in a gas. Temperature isn't a fundamental property. It's a statistical average of the kinetic energy of billions of molecules. In the same way, space-time might be a statistical average of something deeper, something related to the quantum states of strings. This is a radical idea. It says that space and time, the very framework we use to describe everything else, might themselves be emergent phenomena. They might arise from something more fundamental, something that doesn't exist in space and time, because space and time don't exist yet at that level. It's hard to even think about this coherently. How do you describe something that exists before space and time? What does it mean for something to happen if time doesn't exist yet? These are deep conceptual puzzles. Another approach is loop quantum gravity. Loop quantum gravity starts with Einstein's equations and tries to quantize them directly without invoking strings or extra dimensions. In this approach, space is made of discrete loops, quantum states of geometry that link together to form the fabric of spacetime. At large scales, these loops average out to give the smooth spacetime of Einstein's theory. But at the Planck scale, spacetime has a discrete structure. It's grainy, like a fabric woven from threads. Loop quantum gravity predicts that there's a smallest possible volume of space, about 10 to the negative 105 cubic meters. You can't have a region of space smaller than this. It's the quantum of volume, the fundamental pixel of space. In this theory, the Big Bang singularity doesn't exist. Instead of a point of infinite density, the universe bounces. It contracts to a finite minimum size, then expands again. This is called a big bounce. The singularity is replaced by a quantum bounce where space-time has a discrete structure that prevents densities from becoming infinite. Both string theory and loop quantum gravity are speculative. Neither has made testable predictions that we can check with current experiments. They're mathematical frameworks, beautiful and elegant in their own ways, but not yet confirmed by observation. We don't know if either is correct. We don't know if space-time is made of strings, loops, or something else entirely. This is frustrating for physicists. We have equations that work, theories that describe observations, but we're missing the final piece. We're missing the deep understanding of what space-time actually is. Let's think about why this matters. Why should we care whether space-time is fundamental or emergent? Why does it matter if it's continuous or discrete? One reason is that understanding quantum gravity would let us describe what happened at the beginning of the universe. The Big Bang is a singularity in Einstein's equations. At time zero, density and temperature are infinite. The equations break down. They can't tell us what happened at the very first instant. They can't tell us whether there was anything before the Big Bang or what caused it to happen. With a quantum theory of gravity, we might be able to describe the initial conditions of the universe. We might understand whether the Big Bang was truly the beginning of time or whether something existed before. Some quantum gravity theories predict an eternal universe that goes through cycles of expansion and contraction. Others predict a multiverse where Big Bangs happen constantly, creating bubble universes that expand and evolve independently. We don't know which scenario is correct because we don't have a complete theory, but solving the mystery of quantum gravity would give us answers. Another reason this matters is black holes. Black holes are laboratories for extreme physics. They're places where space-time curvature is so strong that quantum effects should be important. And black holes have puzzles that we don't fully understand. One of the biggest is the information paradox. When something falls into a black hole, it seems to disappear. It crosses the event horizon and falls toward the singularity. From outside, you can't see it anymore. You can't retrieve any information about what fell in. All you can measure is the black hole's mass, charge, and spin. Everything else is hidden. But quantum mechanics says information can't be destroyed. It's a fundamental principle. If you know the complete quantum state of a system at one time, you can in principle calculate what it will be at any future time. Information is conserved. It can be scrambled, it can be hidden, but it can't disappear. So what happens to the information that falls into a black hole? Does it really disappear, violating quantum mechanics, or is it somehow preserved? Stephen Hawking showed in the 1970s that black holes aren't completely black. They emit radiation due to quantum effects near the event horizon. This is called Hawking radiation. A black hole slowly evaporates, losing mass over time. Eventually it disappears completely. So where does the information go? If the black hole evaporates and the Hawking radiation is completely random, carrying no information about what fell in, then information is lost. This would be a violation of quantum mechanics. Physicists have debated this for decades. The current consensus is that information is not lost. It's encoded in the Hawking radiation in extremely subtle ways. The radiation looks random, but it actually contains all the information about what fell into the black hole. This information is scrambled in a way that makes it nearly impossible to decode, but it's there. This resolution requires a deep understanding of how quantum mechanics and gravity interact. It requires knowing what spacetime is at the quantum level. There's also the problem of singularities. General relativity predicts singularities in several situations, at the center of black holes, at the beginning of the universe. Singularities are points where the equations give infinite answers, where physics as we understand it breaks down. Most physicists believe singularities aren't real. They're artifacts of using classical equations in situations where quantum effects should be important. A quantum theory of gravity should replace singularities with something else, something finite and describable. Loop quantum gravity replaces the Big Bang singularity with a bounce. String theory replaces black hole singularities with extended objects called fuzzballs. We don't know which picture is correct, but we're confident that singularities are a sign that our current understanding is incomplete. Understanding what replaces them would tell us something fundamental about the nature of space-time. Here's another deep question. Is space-time fundamental or emergent? This might seem like a philosophical question, but it has real physical implications. If space-time is fundamental, if it's the basic fabric of reality, then understanding its properties is the key to understanding the universe. But if space-time is emergent, if it arises from something deeper, then we need to find that deeper layer. We need to understand what space-time is made of in the same way that we understand what matter is made of. There are hints that space-time might be emergent. In string theory, space-time can have different geometries that are mathematically equivalent. Two completely different space-time shapes can describe the same physics. This is called duality. It suggests that space-time geometry isn't fundamental. It's just one way of describing something more basic. In some formulations of string theory, space-time doesn't even appear in the fundamental equations. It emerges as a kind of approximation when you look at large scales. Another hint comes from black hole thermodynamics. Black holes have entropy, a measure of disorder or hidden information. The entropy of a black hole is proportional to the area of its event horizon, not its volume. This is strange. If you think about ordinary matter, entropy depends on volume. A box twice as large can hold twice as much stuff and has twice as much entropy. But a black hole's entropy depends on its surface area. It's as if all the information about what's inside the black hole is encoded on its surface. This led to an idea called the holographic principle. The holographic principle says that the information content of any region of space can be described by information on the boundary of that region. It's like a hologram, where a two-dimensional surface contains all the information needed to reconstruct a three-dimensional image. If the holographic principle is correct, then space-time might be like a hologram. The three-dimensional space we experience might be a projection of information stored on a two-dimensional boundary. Space itself might be an illusion, a useful description that emerges from more fundamental quantum information. This is mind-bending. It says that the three dimensions of space we move through might not be fundamental. They might be emergent, like the image in a hologram. The real fundamental description might be in terms of quantum information on a distant boundary. We don't fully understand this yet. The holographic principle works in certain mathematical models, but we don't know how to apply it to the real universe. We don't know where the boundary is or what the fundamental quantum information looks like. But the idea is compelling. It suggests that space-time is not the final answer. It's a useful approximation, a way of organizing information, but not the deepest level of reality. Let's think about what it would mean if space-time is quantized, if there's a smallest unit of space and time. The Planck length is about 10 to the negative 35 meters. That's 20 orders of magnitude smaller than an atomic nucleus. It's so small that we have no way to probe it directly. Our most powerful particle accelerators can't reach energies high enough to see structure at the Planck scale. To build an accelerator that could, you'd need a machine this size of the galaxy. So we can't directly test whether spacetime is quantized at the Planck length. But there might be indirect ways to test this. If spacetime is discrete at tiny scales, it might affect how particles behave at very high energies. Ultra-high energy cosmic rays, particles from space that hit Earth's atmosphere with enormous energies, might show subtle effects if spacetime has a granular structure. We haven't seen any such effects yet, but we're looking. Another possibility is that quantum structure of spacetime might leave an imprint in gravitational waves. The collisions of black holes generate gravitational waves that we can detect. If spacetime is quantized, these waves might have subtle features that differ from what smooth spacetime predicts. We're analysing the data from LIGO and other detectors to see if any such features exist. There's also the possibility of cosmological tests. The cosmic microwave background, the afterglow of the Big Bang, might carry signatures of quantum gravity effects from the very early universe. When the universe was a fraction of a second old, it was so small and so dense that quantum gravity effects should have been important. Those effects might have left imprints in the CMB that we could detect with sensitive enough instruments. Several experiments are looking for these signatures, but here's the frustrating reality. Quantum gravity effects are so small at accessible energies that they might be impossible to detect with any foreseeable technology. The Planck energy, where quantum gravity becomes important, is about 10 to the 19 GeV. The Large Hadron Collider reaches about 10 to the 4 GeV. We're 15 orders of magnitude away. It's like trying to understand atoms by throwing rocks at each other. The energies are just too low, so we might be stuck with indirect evidence and theoretical arguments. This is unusual in physics. Usually theory and experiment go hand in hand. You make a theoretical prediction, you design an experiment to test it, the experiment tells you if you're right or wrong, and you refine your theory accordingly. But with quantum gravity, the experiments we'd need are beyond our reach. We're forced to rely on mathematical consistency, on making sure our theories don't give nonsensical answers, on checking that they agree with what we already know at lower energies. It's like trying to navigate in the dark with only a compass and a map you're not sure is accurate. Some physicists find this situation exciting. It's a chance to think deeply about the fundamental nature of reality without being constrained by immediate experimental tests. You can explore radical ideas, follow the mathematics wherever it leads, and see what the universe could be like. Others find it frustrating. Without experimental guidance, how do you know if you're on the right track? You could spend decades developing a theory that's mathematically beautiful, but has nothing to do with reality. There's no way to know until you can test it. This brings us to another aspect of the mystery. What is time? We've been talking about space-time as if space and time are similar, just different dimensions of the same thing. Einstein's equations treat them that way. In special relativity, space and time mix together. What one observer calls time, another observer moving at a different speed will see as a mixture of space and time. But there's a fundamental difference. You can move freely through space. You can go forward, backward, left, right, up, down. But you can only move forward through time. You can't go backward. You can't stop. Time seems to flow in one direction. This is called the arrow of time, and it's deeply mysterious. The fundamental laws of physics don't distinguish between forward and backward in time. If you watch a video of planets orbiting the sun, you can't tell if the video is playing forward or backward. Both directions are consistent with Newton's laws and Einstein's equations. The laws work the same way in both directions, and yet our experience of time is clearly directional. We remember the past, not the future. We see glasses breaking but never unbreaking. We see entropy increasing, disorder spreading. Time has an arrow. The arrow of time is usually explained through entropy and the second law of thermodynamics. Entropy measures disorder. The second law says that in a closed system, entropy always increases or stays the same. It never decreases. This gives time a direction. The future is the direction in which entropy increases. But this explanation just pushes the mystery back a step. Why did the universe start with such low entropy? The Big Bang was a state of incredibly low entropy, incredibly high order. All the matter and energy in the universe compressed into a tiny region. As the universe expands, entropy increases. Stars form, burn, die. Black holes form and evaporate. Entropy goes up. But why did it start so low? Why was the initial state of the universe so ordered? We don't know. Understanding the beginning of the universe requires understanding quantum gravity. It requires knowing what space-time is at the Planck scale, at the first fraction of a second after the Big Bang. If we can understand that, we might understand why entropy was so low initially and why time has an arrow. Some theories suggest that time itself might be emergent, that it might arise from something more fundamental, just like space-time might. At the deepest level, there might be no time. Time might be an approximation that only makes sense at large scales when you average over many quantum events. This is hard to wrap your mind around. We experience time as fundamental. It's the framework in which we think. Events happen in sequence. Causes precede effects. But maybe that's just how things appear at our scale. Maybe at the fundamental level, the Planck scale, there's no time. There's just a quantum state, a mathematical object that encodes all possibilities. Time emerges when you coarse grain, when you zoom out and look at large-scale averages. It's like how the flow of water in a river emerges from the motion of individual molecules. Each molecule just bounces around randomly, but when you average over billions of molecules, you see a smooth flow. If time is emergent, then what does it emerge from? What's the more fundamental thing that gives rise to time? Different approaches to quantum gravity have different answers. In string theory, time might emerge from the dynamics of strings and branes in higher dimensional spaces. In loop quantum gravity, time might emerge from the evolution of quantum states of geometry. In some approaches based on the holographic principle, time might be related to the growth of entanglement between quantum systems. We don't know which picture is correct, or if any of them are. There's also the possibility that space-time is fundamentally discrete, not just in space but in time as well. Maybe time doesn't flow smoothly. Maybe it comes in indivisible chunks, quanta of time. The Planck time is about 10 to the negative 44 seconds. Maybe that's the smallest meaningful duration. Maybe time is like frames in a movie. Each frame shows a slightly different configuration, and when you play them fast enough it looks like smooth motion. But really there are discrete frames. If this is true, then asking what happens between two adjacent moments in time is meaningless, like asking what happens between two frames of a movie. There is no between, there are just discrete moments. This would solve some conceptual problems. One of the paradoxes of motion, known since ancient Greek philosophy, is Zeno's paradox. If space and time are infinitely divisible, then to move from point A to point B, you first have to get halfway there. Then you have to get halfway from the midpoint to B, then halfway again, and so on. You have to complete an infinite number of steps, which seems impossible. How do you complete an infinite number of tasks in a finite time? If space-time is fundamentally discrete, this paradox dissolves. There aren't an infinite number of steps. There's a finite number of Planck-length steps in any journey, and a finite number of Planck time intervals. Motion isn't paradoxical, it's just a sequence of discrete jumps. But discrete space-time creates its own problems. How do the discrete chunks connect? What determines the shape of space-time on scales larger than the Planck length? How do you get the smooth, continuous space-time of Einstein's equations from an underlying discrete structure? These are active areas of research. Loop quantum gravity and some other approaches have proposals, but none are fully worked out. Let me give you an analogy that might help. Think about water. At large scales, water seems like a continuous fluid. You can pour it, it flows, it has smooth surfaces. The equations that describe water treat it as a continuum. You can zoom in arbitrarily far and the equations still work, but we know water isn't really continuous. It's made of molecules. At small scales, water is discrete. It's individual H2O molecules bouncing around. The smooth fluid behavior emerges when you average over trillions of molecules. Spacetime might be like this. At large scales, it seems smooth and continuous. Einstein's equations describe it as a continuum, but at the Planck scale, it might be discrete, made of fundamental units, quanta of geometry. The smooth space-time we experience emerges when you average over huge numbers of these quantum units. This is the dream of quantum gravity. To find the molecular structure of space-time, the fundamental atoms of space and time, and to show how Einstein's smooth space-time emerges from them. Now let's talk about what we actually observe and how it connects to these deep questions. We've detected gravitational waves, ripples in space-time. LIGO detected the first gravitational waves in 2015 from two black holes colliding 1.3 billion light-years away. The signal lasted less than a second. It was a chirp, a rising frequency as the black holes spiraled inward, merged, and settled into a single larger black hole. The amplitude of the waves when they reached Earth was incredibly small. They stretched and squeezed space by less than 1,000th the diameter of a proton. But LIGO detected them. Since then, we've detected dozens of gravitational wave events, black hole mergers, neutron-star mergers, events across billions of light-years. Each detection confirms Einstein's theory. The waveforms match the predictions of general relativity with extraordinary precision. We can extract information about the masses and spins of the merging objects. We can test whether black holes behave as Einstein predicted. So far, everything matches. General relativity passes every test. But here's what's interesting. Gravitational waves are oscillations in space-time itself. They're not waves travelling through space-time like sound waves through air. They're waves of space-time. Space itself is oscillating. When a gravitational wave passes through you, the distance between your atoms changes. You get stretched in one direction and squeezed in another. Then the wave passes and you return to normal. You don't feel it because everything is being stretched and squeezed together, including the atoms in your body and any measuring device you might use. LIGO detects gravitational waves using laser interferometry. It has 2 arms, each 4 kilometers long, arranged in an L shape. Laser light bounces back and forth in each arm. When a gravitational wave passes through, one arm gets slightly longer and the other slightly shorter. This changes the time it takes light to travel down each arm. When the light beams recombine, they interfere. The interference pattern tells you how much the arm length's changed. By measuring this with incredible precision, LIGO can detect gravitational waves. What? Does this tell us about space-time? It tells us that space-time is real. It's not just a mathematical abstraction. It's a physical thing that can oscillate, carry energy, and be detected. Gravitational waves carry energy away from the systems that produce them. When 2 black holes merge, about 3 solar masses of energy is radiated as gravitational waves. That's 3 times the mass of the Sun converted entirely into energy and carried away by space-time oscillations. Einstein's equation E equals mc squared applies. The mass of the final black hole is less than the sum of the 2 initial black holes because energy was radiated away. This confirms that space-time has properties. It can store energy. It can transmit forces. It behaves like a field. But we still don't know what it is. We don't know if it's fundamental or emergent. We don't know if it's continuous or discrete at tiny scales. Gravitational wave astronomy is giving us new tools to probe these questions. As detectors become more sensitive, we might see effects that hint at the quantum nature of space-time. We might detect tiny deviations from Einstein's predictions that tell us something about quantum gravity. Another observation that's relevant is the accelerating expansion of the universe. In 1998, astronomers discovered that the universe isn't just expanding, it's accelerating. Distant galaxies are moving away from us faster and faster. This was completely unexpected. Gravity should slow down the expansion. The mutual gravitational attraction of all the matter in the universe should act as a brake, gradually slowing the expansion over time. Instead, the expansion is speeding up. To explain this, physicists introduced dark energy. Dark energy is a form of energy that fills all of space and pushes space apart. It has negative pressure. Normal matter and energy have positive pressure. They clump together. Dark energy does the opposite. It pushes everything apart. About 68% of the total energy in the universe is dark energy. We don't know what it is. The simplest explanation is that it's the energy of empty space itself, what's called vacuum energy, or the cosmological constant. Here's where things get strange. Quantum field theory predicts that empty space should have energy. Even in a perfect vacuum with no particles, quantum fields fluctuate. These fluctuations have energy. When you calculate how much energy empty space should have according to quantum field theory, you get an answer. The problem is, the answer is wrong by about 120 orders of magnitude. It's the worst prediction in the history of physics. Quantum field theory predicts that the vacuum energy should be enormous, about 10 to the 120 times larger than what we observe. If this were true, the universe would have been ripped apart instantly. Space would expand so fast that atoms couldn't form, stars couldn't form, galaxies couldn't form. Nothing would exist. But we observe a tiny cosmological constant, about 10 to the negative 120 in Planck units. It's small enough that the universe can exist, but large enough to cause accelerating expansion. This is called the cosmological constant problem, and it's one of the deepest mysteries in physics. Why is the vacuum energy so small? There must be some mechanism that cancels out the enormous quantum contributions, leaving only a tiny residual. But we don't know what that mechanism is. Understanding it requires understanding the nature of space-time at the quantum level. It requires knowing what empty space really is. Some theories suggest that the vacuum energy might be related to the number of dimensions. String theory requires extra dimensions beyond the 3 space dimensions we experience. These extra dimensions might be compactified, curled up at tiny scales. The way they're compactified affects the vacuum energy. Maybe the observed cosmological constant is a consequence of the particular way extra dimensions are arranged. But we don't know if extra dimensions exist, and if they do, we don't know how they're compactified. Another approach is the anthropic principle. Maybe the cosmological constant has to be small for life to exist. In a universe with a large cosmological constant, structure wouldn't form. No galaxies, no stars, no planets, no life. We observe a small cosmological constant because we exist to observe it. In universes with large cosmological constants, there's no one to ask the question. This is a controversial explanation. It seems to give up on finding a dynamical reason for the observed value. It says we just got lucky, or that there are many universes with different cosmological constants, and we happen to be in one where life is possible. The multiverse idea is connected to this. Some versions of string theory and some models of cosmic inflation predict that there are many universes, each with different physical constants, different numbers of dimensions, different vacuum energies. Most of these universes are sterile, devoid of structure, but a few by chance have conditions that allow complexity to develop. We find ourselves in one of those universes because that's the only kind where observers can exist. This is philosophically troubling for many physicists. It seems to abandon the goal of explaining why the universe has the properties it does. Instead of finding a unique theory that predicts the cosmological constant, it says there are many possible values and we observe this one by selection bias. But if the multiverse is real, if it's a consequence of our fundamental theories, then we have to take it seriously. Understanding whether the multiverse exists requires understanding quantum gravity and the nature of space-time. Let's come back to black holes. Black holes are the ultimate laboratories for testing our understanding of space-time. They're regions where curvature is so extreme that our theories are pushed to their limits. At the event horizon, space-time is curved but still smooth. Einstein's equations work fine, but at the singularity the equations break down. They predict infinite curvature, infinite density. This is a signal that we're using the wrong tools. We need a quantum theory of gravity to describe what happens at the singularity. Stephen Hawking's discovery of black hole radiation was a breakthrough in understanding how quantum mechanics and gravity interact. Hawking showed that if you consider quantum fields near the event horizon, black holes aren't completely black. They emit particles. The mechanism is subtle. Quantum fluctuations near the horizon create particle-antiparticle pairs. One particle falls into the black hole, the other escapes. From far away, it looks like the black hole is emitting radiation. This is Hawking radiation. The temperature of Hawking radiation is inversely proportional to the black hole's mass. For a solar mass black hole, the temperature is about 60 nanokelvins, much colder than the cosmic microwave background. So stellar mass black holes don't actually evaporate. They absorb more radiation from the CMB than they emit. But in the far future, after the CMB cools down, black holes will start evaporating. Smaller black holes evaporate faster. A black hole with the mass of a mountain would evaporate in about the age of the universe. A microscopic black hole would evaporate almost instantly in a burst of radiation. Hawking radiation raises the information paradox. When a black hole evaporates, where does the information go? If you throw a book into a black hole, all the information in the book seems to disappear. The black hole's mass increases slightly, but you can't tell what you threw in. All black holes with the same mass, charge, and spin look identical. Then the black hole evaporates via Hawking radiation. If the radiation is completely random, carrying no information about what fell in, then the information in the book is lost forever. This violates quantum mechanics, which says information is always conserved. The resolution seems to be that Hawking radiation is not completely random. It's correlated in extremely subtle ways. The information is there, encoded in the radiation, but it's scrambled so thoroughly that it's nearly impossible to decode. Imagine you have a book, you burn it, you scatter the ashes, and you claim that all the information in the book is still present in the positions and quantum states of the ash particles and the photons from the fire. Technically, this is true. In principle, you could reconstruct the book if you measured the quantum state of every particle. But in practice, it's impossible. The information is there, but it's hopelessly scrambled. Black holes do something similar. They scramble information maximally. When you throw something into a black hole, the information gets spread over the entire event horizon in a complicated way. Then it slowly leaks out via Hawking radiation. After the black hole evaporates completely, all the information is in the radiation, but you'd need to collect and analyze every single photon to reconstruct what fell in. This is the best current understanding, but it's not fully worked out. We don't have a complete calculation showing exactly how the information is encoded in the radiation. That requires a full theory of quantum gravity. There's a related puzzle about the interior of black holes. According to general relativity, if you fall into a black hole, you don't feel anything special as you cross the event horizon. Space is curved, but locally it looks normal. You're in freefall, weightless, following a geodesic. You don't even know you've crossed the point of no return until you try to turn around and realize you can't. Then you fall toward the singularity, experiencing stronger and stronger tidal forces that eventually tear you apart. This is called spaghettification. The gravitational gradient is so steep that your feet, close to the singularity, are pulled much harder than your head. You get stretched into a long, thin strand. But there's a problem. The information paradox suggests that information can't fall into the black hole and remain hidden. It has to be accessible from outside. This leads to the firewall paradox. If information is somehow encoded on the event horizon, then quantum mechanics predicts that the horizon should be a violent, high-energy place. When you try to cross it, you hit a firewall, a sheet of intense radiation that incinerates you instantly. But this contradicts general relativity, which says the horizon is smooth and you can cross it without noticing. This is a real paradox. General relativity and quantum mechanics give contradictory predictions about what happens at the event horizon. We don't know which is right. Most physicists suspect that the resolution requires understanding quantum gravity. Maybe space-time near the event horizon has a quantum structure that changes the picture. Maybe the smooth horizon of classical general relativity is an approximation that breaks down when you account for quantum effects properly. One proposal is that black holes don't have sharp event horizons. Instead, they have fuzzy quantum surfaces. Information that falls in doesn't cross a definite boundary. It gets spread out in a quantum way, entangled with the radiation that escapes. You can't say precisely when something crosses into the black hole. The interior and exterior are quantum mechanically entangled. This is speculative, but it's the kind of idea that might emerge from a full theory of quantum gravity. Another aspect of black holes that's mysterious is their entropy. Black holes have entropy proportional to the area of their event horizon. This was discovered by Jacob Bekenstein and Stephen Hawking in the 1970s. The entropy is enormous. A black hole with the mass of the Sun has entropy about 10 to the 77, far more than any normal object. Entropy measures the number of microstates, the number of different ways you can arrange the fundamental constituents to produce the same macroscopic properties. For a gas, entropy counts how many ways you can arrange the molecules to get the same temperature and pressure. For a black hole, entropy should count how many ways you can arrange whatever space-time is made of to produce the same mass, charge, and spin. But we don't know what space-time is made of, so we can't count the microstates directly. String theory has had some success in calculating black hole entropy for certain special black holes. The calculation involves counting the quantum states of strings and branes that form the black hole. The answer matches the Bekenstein-Hawking formula. This is considered one of string theory's successes. It suggests that string theory might be on the right track, but the calculation only works for certain highly symmetric black holes. We don't have a general formula for all black holes. Loop quantum gravity also has proposals for calculating black hole entropy. The idea is that the horizon is made of discrete quantum loops, and you count how many ways you can arrange the loops to get the observed area. The counting gives something close to the Bekenstein-Hawking formula, which is encouraging. But again, the calculations are preliminary. We don't have a complete picture. The fact that black hole entropy depends on area rather than volume is a big clue. It suggests that the information inside a black hole is somehow encoded on its surface. This is the basis of the holographic principle, which I mentioned earlier. The holographic principle says that the information content of any region of space is proportional to the area of the boundary, not the volume. This is completely unlike anything we're used to. For ordinary objects, information scales with volume. A hard drive twice as large can store twice as much data. But if the holographic principle is correct, the maximum information you can store in a region is proportional to the surface area of that region, measured in Planck units. This has profound implications. It suggests that our three-dimensional universe might actually be a holographic projection of information stored on a two-dimensional boundary. We live in what seems like 3D space, but the fundamental description might be in terms of 2D quantum information. This is hard to visualize. How can our 3D experience emerge from 2D information? The mathematics works in certain models, but we don't have a complete physical picture. One of the cleanest examples is the AD-CFT correspondence, discovered by Juan Maldacena in 1997. AD stands for anti-de Sitter space, a particular geometry of spacetime with negative curvature. CFT stands for conformal field theory, a type of quantum field theory. Maldacena showed that a theory of gravity in AD space is mathematically equivalent to a quantum field theory without gravity living on the boundary of that space. The boundary is one dimension lower, so a theory of gravity in 5D AD space is equivalent to a 4D quantum field theory. This is a precise realization of the holographic principle. Everything that happens in the bulk, the interior 5D space, can be described by quantum field theory on the 4D boundary. Gravitational phenomena like black holes correspond to thermal states in the boundary theory. The growth and evaporation of black holes corresponds to thermalization and cooling in the boundary theory. This correspondence has been checked in thousands of calculations, and it always works. It's one of the most important discoveries in theoretical physics in the past few decades. But there's a catch. The AD-CFT correspondence works in AD space, which has negative curvature. Our universe has positive curvature, or at least it's close to flat with a tiny positive cosmological constant. We don't have a holographic description of our actual universe. We don't know where the boundary is or what the boundary theory looks like. AD-CFT is a proof of concept. It shows that holography can work, that gravity can emerge from quantum field theory, that space-time might be a holographic projection. But we don't yet know how to apply it to the real universe. Despite all these puzzles, general relativity remains incredibly successful. Every test we can perform confirms its predictions. The orbit of Mercury matches general relativity's prediction. Light bending around the Sun matches. Gravitational time dilation matches. Gravitational waves match. Black hole shadows match. The expansion of the universe matches. There's no observation that contradicts general relativity within its domain of applicability. The theory works perfectly when spacetime curvature is weak or moderate and quantum effects are negligible. The problems only appear in extreme situations, at the centre of black holes where curvature diverges, at the Big Bang where the entire universe was compressed to a point, in situations where both gravity is strong and quantum effects are important. These are the places where we expect general relativity to break down and be replaced by something else. But in everyday situations, even in fairly extreme situations like neutron stars or gravitational wave sources, general relativity is correct. This brings us to an important philosophical point. When we say we don't understand what space-time is, we need to be careful about what we mean. We understand space-time extremely well in a practical sense. We can describe its behaviour mathematically. We can predict how it curves in response to matter and energy. We can calculate gravitational wave signals. We can simulate the formation of black holes on computers. We can use general relativity to design GPS systems and predict the motion of planets. In every operational sense, we understand space-time. What we don't understand is the deeper ontological question. What is it? Is it fundamental or emergent? Is it continuous or discrete? What happens at the Planck scale? These are questions about the nature of reality at the deepest level. They're not practical questions. Answering them won't let you build a better GPS or predict planetary orbits more accurately. But they're profound questions about what the universe is made of. This is similar to other situations in physics. We understand electromagnetism extremely well. Maxwell's equations describe how electric and magnetic fields behave. We can predict the motion of charged particles, design circuits, build motors and generators, transmit radio waves. But what is an electromagnetic field? Is it a disturbance in some medium? Is it a fundamental entity? Maxwell thought electromagnetic waves were vibrations in a medium called the luminiferous ether. He tried to build mechanical models of the ether, but the ether doesn't exist. Electromagnetic fields are fundamental as far as we know. They're not vibrations in anything, they just are. Or take quantum mechanics. We can calculate the behaviour of atoms, molecules, electrons. We can predict the spectrum of hydrogen, the structure of DNA, the properties of semiconductors. Quantum mechanics is the most precisely tested theory in history. But what is the wave function? Is it a real physical thing, or just a mathematical tool for calculating probabilities? When you measure a quantum system, does the wave function collapse, or do multiple outcomes exist in parallel universes? These are deep questions about the nature of reality, and physicists disagree about the answers. The mystery of space-time is similar. We can use Einstein's equations to make predictions, and the predictions work. But what is space-time itself? The answer might turn out to be that space-time is fundamental, an irreducible entity that doesn't need further explanation. Or it might turn out to be emergent, arising from something more basic. We don't know yet. Let's think about what experiments or observations might help us figure this out. One possibility is detecting quantum gravitational effects. If space-time is quantized, there might be tiny corrections to the predictions of classical general relativity. These corrections would be incredibly small at accessible energies, but they might be detectable in precision experiments. For example, the motion of test masses in space might show tiny deviations from what general relativity predicts if space-time has a discrete structure. NASA has proposed missions like LISA, a space-based gravitational wave detector that might be sensitive enough to see such effects. Another possibility is studying the early universe. During cosmic inflation, when the universe was a tiny fraction of a second old, quantum fluctuations were stretched to enormous scales. These fluctuations seeded the formation of galaxies and large-scale structure. The pattern of fluctuations in the cosmic microwave background carries information about the inflationary epoch. If quantum gravity effects were important during inflation, they might have left an imprint that we can detect. One specific prediction is the presence of primordial gravitational waves. Inflation should have produced gravitational waves in addition to density fluctuations. These gravitational waves would create a particular pattern in the polarization of the cosmic microwave background called B-modes. Several experiments are searching for B-mode polarization. If we detect it, we'll learn about the energy scale of inflation. If that energy scale is high enough, it means quantum gravity effects were important, and we might be able to extract information about quantum spacetime from the data. There's also the possibility of detecting quantum gravitational effects in black hole mergers. When two black holes collide, they form a single black hole that rings down, oscillating before settling into a stable configuration. These oscillations produce gravitational waves with specific frequencies that depend on the mass and spin of the final black hole. If space-time has quantum structure, the ring down might have subtle features that differ from classical predictions. As gravitational wave detectors become more sensitive, we might be able to see these features. Another approach is to look for violations of fundamental symmetries. In classical general relativity, physics is the same in all directions, and it's the same at all points in space and time. These symmetries are called Lorentz invariants and translational invariants. Some approaches to quantum gravity predict tiny violations of these symmetries. If we detect such violations, it would be a smoking gun for quantum gravity. Experiments with ultra-high energy cosmic rays, gamma-ray bursts, and precision atomic clocks are searching for these violations. So far, nothing has been found, but the searches continue. There's also theoretical progress. Even without direct experimental tests, physicists can make progress by demanding mathematical consistency. A theory of quantum gravity has to reproduce general relativity at low energies, and quantum mechanics at weak gravitational fields. It has to avoid mathematical inconsistencies like infinite answers in physical calculations. It has to preserve principles like conservation of energy and conservation of information. These constraints are powerful. They rule out many possible theories. String theory satisfies many of these constraints. It's mathematically consistent. It includes gravity. It reproduces general relativity in the appropriate limit. It has quantum mechanics built in from the start. The problem is that string theory is not unique. There are many different versions, called string vacua, each describing a different possible universe with different properties. We don't know which vacuum describes our universe, or if any of them do. String theory also requires extra dimensions, which we haven't observed. The extra dimensions could be compactified at tiny scales, too small to detect directly, but this makes the theory hard to test. Loop quantum gravity avoids extra dimensions. It works in ordinary four-dimensional spacetime. It provides a picture of what spacetime looks like at the Planck scale, a network of discrete quantum loops. But loop quantum gravity is less developed than string theory in some ways. It's harder to extract predictions for particle physics. It's not clear how to include all the forces of nature in a unified way. Researchers are working on these problems, but progress is slow. There are other approaches as well. Causal set theory treats space-time as a discrete set of points with causal relationships between them. Asymptotic safety proposes that gravity might be quantum mechanically well-behaved after all without needing strings or loops. Emergent gravity theory suggests that gravity arises from thermodynamics and quantum entanglement. Each approach has strengths and weaknesses. None has emerged as the clear winner. This might seem frustrating. We have multiple competing theories, none of which has made testable predictions that distinguish it from the others. But this is normal in science when you're pushing the boundaries. Before atoms were discovered, there were multiple competing theories about the structure of matter. Before quantum mechanics was developed, there were multiple attempts to explain atomic spectra. Eventually, experiments narrowed down the possibilities and guided theorists toward the correct answer. We're in a similar situation now with quantum gravity. We're exploring the theoretical landscape, developing mathematical tools, and waiting for experiments to give us clues. One thing that gives physicists confidence is that the different approaches to quantum gravity are starting to converge in some ways. String theory and loop quantum gravity, which initially seemed completely different, are now finding connections. Some string theory calculations produce results that look like loop quantum gravity. Some loop quantum gravity calculations produce results that look like string theory. The holographic principle, which emerged from string theory, is now being explored in other contexts. There are hints that all these approaches might be describing the same underlying reality from different perspectives. This is how physics often progresses. You have different theories that seem incompatible at first. Then you realize they're different approximations or different perspectives on the same thing. Newton's laws and Einstein's relativity seem different, but Einstein's theory reduces to newtons when speeds are much slower than light. Particle descriptions and wave descriptions of quantum mechanics seemed incompatible, but they're unified in quantum field theory. Maybe the various approaches to quantum gravity will eventually be unified into a single coherent picture. Let's think about what the answer might look like. If space-time is emergent, what could it emerge from? One possibility is quantum entanglement. Entanglement is a uniquely quantum phenomenon where two particles can be correlated in ways that have no classical explanation. When you measure one particle, you instantly know something about the other, no matter how far apart they are. Einstein called this spooky action at a distance, and it troubled him deeply. But entanglement is real. It's been demonstrated countless times in experiments. Recent work suggests that quantum entanglement and spacetime geometry might be intimately connected. In the AD-CFT correspondence, it turns out that entanglement in the boundary quantum field theory corresponds to geometric connections in the bulk spacetime. Regions that are highly entangled in the boundary theory are connected by smooth spacetime in the bulk. Regions with little entanglement are disconnected or separated by large distances. This suggests that spacetime geometry might be woven from quantum entanglement. The famous slogan is "Spacetime is entanglement." If this is correct, then understanding spacetime means understanding the pattern of quantum entanglement in the underlying quantum state. Space itself would be an emergent description of how quantum systems are entangled with each other. Distance would measure the difficulty of sending quantum information from one system to another. A smooth, flat spacetime would correspond to a highly entangled quantum state. A curved spacetime would correspond to a different pattern of entanglement. A black hole would be a region where entanglement is structured in a particular way. This is a radical idea. It says that the three dimensions of space we move through are not fundamental. They're a convenient description that emerges when quantum systems are entangled in certain ways. If you could see the universe at the fundamental level, you wouldn't see space at all. You'd see a quantum state, a vast network of entangled degrees of freedom. Space emerges when you coarse grain, when you ignore the details and look at large-scale patterns. Another possibility is that space-time emerges from computation or information processing. Some physicists have proposed that the universe is fundamentally a quantum computer, and space-time is the interface that emerges from the computation. In this view, the fundamental degrees of freedom are qubits, quantum bits of information. The laws of physics are algorithms that specify how qubits interact and evolve. Space-time geometry emerges as a description of the information flow between qubits. This is inspired by developments in quantum information theory. Researchers have discovered deep connections between quantum information, thermodynamics, and gravity. Black holes, for example, can be understood as quantum information processors that scramble information maximally. The growth of black hole entropy corresponds to the spreading of quantum entanglement. The second law of thermodynamics, which says entropy always increases, can be understood as a statement about information flow in quantum systems. If space-time is fundamentally about information and computation, then the question, what is space-time made of, has an answer. It's made of quantum information. The fabric of space-time is woven from qubits, from quantum states and their correlations. This is appealing because information is fundamental in quantum mechanics. The wave function is information about the system. Measurements gain information. Entanglement is about correlations, which are informational relationships. Maybe everything reduces to information at the deepest level. But there are conceptual challenges. If space-time emerges from information, whose information is it? Information is usually relative. One observer might have information that another doesn't. Does space-time exist differently for different observers? In quantum mechanics, different observers can disagree about the state of a system before they communicate and compare notes. Does this mean they experience different space-times? These are difficult questions that researchers are grappling with. There's also the question of whether emergent space-time can fully recover all the features of Einstein's theory. Emergence usually involves approximation. When you describe water as a fluid, you're ignoring the molecular structure. The fluid description is an approximation that works at large scales. Could space-time be similar? At the Planck scale, the approximation breaks down, and you see the underlying quantum structure. At larger scales, space-time looks smooth and continuous, and Einstein's equations work perfectly. If this is right, then there might be small corrections to Einstein's equations that appear when you account for the quantum structure. These corrections would be incredibly tiny in most situations, too small to detect. But in extreme situations like the Big Bang or black hole singularities, the corrections become important. They might resolve the singularities, replacing them with quantum bounces or other structures. They might explain the initial conditions of the universe or the final state of evaporating black holes. Some researchers are trying to derive Einstein's equations from more fundamental principles. If space-time is emergent, then gravity should be emergent too. Eric Verlinde has proposed that gravity is an entropic force, a statistical effect arising from the tendency of systems to maximize entropy. In this view, what we call gravity is really just the universe evolving towards states of higher entropy. Mass curves space-time because that's the configuration with maximum entropy, given the constraints. This is speculative and controversial, but it's an example of how physicists are thinking outside the box. Let's consider what it would mean if we solved this mystery. If we had a complete theory of quantum gravity, a full understanding of what space-time is at the deepest level, what would we gain? First, we'd understand the beginning of the universe. We could describe what happened at the Big Bang or whether something existed before. We could explain why the universe started in a low entropy state and why time has an arrow. We might learn whether our universe is unique or one of many in a multiverse. Second, we'd understand black holes completely. We'd know what happens at singularities. We'd resolve the information paradox definitively. We'd know whether firewalls exist or whether you can safely fall through an event horizon. We'd understand how black holes store entropy and what the microstates are. We might even learn whether black holes are connected to other regions of space or other universes through wormholes. Third, we'd understand the cosmological constant problem. We'd know why the vacuum energy is so small and whether it's a constant or evolving. We'd know whether dark energy is truly Einstein's cosmological constant or something more exotic. This might tell us about the ultimate fate of the universe. Will the expansion continue accelerating forever, leading to a cold, dark, empty future? Or will something change? Fourth, we'd know whether phenomena like wormholes and time travel are possible. General relativity allows these things mathematically, but they require exotic matter with negative energy density. Does such matter exist? Can it be created? Or does quantum gravity forbid these solutions? A complete theory would tell us the answer. It would tell us whether faster-than-light travel is possible through shortcuts in space-time, or whether we're forever limited to the speed of light. Fifth, we might find connections to other mysteries in physics. The unification of forces, the origin of mass, the nature of dark matter, these might all be connected to quantum gravity. String theory, for example, attempts to unify all forces in a single framework. If string theory is correct, solving quantum gravity means solving particle physics too. We'd understand why there are four forces, why particles have the masses they do, and why the universe has the structure it has. Finally, there's the philosophical impact. Understanding space-time at the deepest level would change how we think about reality. If space and time are emergent, if they arise from quantum entanglement or information, then our everyday experience is a kind of illusion. The world we perceive is a coarse-grained approximation of something far stranger. This would be a shift comparable to Copernicus showing that Earth isn't the centre of the universe, or Darwin showing that humans evolved from other species. It would change our place in the cosmos and our understanding of what it means to exist. But we need to be honest about the timeline. Solving quantum gravity is hard. It might take decades or centuries. It might require experimental breakthroughs that seem impossible today. Or it might require a conceptual leap that we haven't made yet, a new way of thinking about the problem that makes everything click into place. History shows that progress in physics is unpredictable. Sometimes problems that seem impossibly hard are solved quickly by an unexpected insight. Sometimes progress takes generations. Consider the history of atomism. The idea that matter is made of atoms goes back to ancient Greece, to Democritus and Leucippus. But for over 2,000 years it remained speculative. There was no way to test it. Some philosophers believed in atoms, others didn't. It wasn't until the early 1900s with experiments on Brownian motion and cathode rays that atoms were confirmed to exist. Then within a few decades we understood atomic structure, quantum mechanics, and nuclear physics. The breakthrough came when we had the right experimental tools and the right theoretical framework. We might be in a similar situation with quantum gravity. We're developing the mathematical tools, exploring different theoretical frameworks, and slowly improving our experimental capabilities. At some point the pieces will come together. We'll have a theory that works mathematically and makes testable predictions. We'll build instruments sensitive enough to test those predictions, and we'll understand spacetime at the deepest level. Now let's think about the practical implications of not knowing what spacetime is. Does it matter for everyday life? For most purposes, no. General relativity works perfectly well for everything we need. GPS satellites account for time dilation. We can predict the orbits of planets centuries into the future. We can detect gravitational waves from billions of light years away. The fact that we don't know whether spacetime is made of strings or loops or quantum information doesn't affect any of these applications. But there are situations where it might matter. One is the development of future technology. If we understood quantum gravity, we might discover new phenomena that could be exploited. Maybe there are ways to manipulate space-time that we haven't imagined. Maybe there are shortcuts through space that become possible at high enough energies. Maybe there are new forms of energy or new states of matter that exist only when quantum gravity effects are important. We won't know until we have the complete theory. Consider what happened with quantum mechanics. In the 1920s, quantum mechanics was a purely theoretical development. Physicists were trying to understand the behavior of atoms and the spectrum of light emitted by hydrogen. It seemed like an abstract mathematical exercise with no practical applications. But within decades, quantum mechanics led to transistors, lasers, nuclear energy, MRI machines, and countless other technologies. The entire modern world runs on quantum mechanics. None of it would have been possible without understanding how electrons behave in atoms. Quantum gravity might be similar. Right now it seems abstract and far removed from practical concerns. But understanding it might unlock technologies we can't imagine. Maybe not in our lifetimes, maybe not for centuries, but eventually. The history of physics shows that deep theoretical understanding eventually leads to applications. Maxwell's equations, developed to understand the abstract behavior of electric and magnetic fields, led to radio, television, and wireless communication. Einstein's relativity, developed to understand the nature of space and time, led to GPS and nuclear energy. There's also the intellectual value. Humans are curious. We want to understand the universe. This drive to understand is part of what makes us human. We've always looked at the sky and asked questions. What are the stars? Why does the sun move across the sky? What is the Earth made of? These questions led to astronomy, physics, chemistry, and all of science. The question, what is space-time, is in this same tradition. It's a fundamental question about the nature of reality. Some people argue that spending resources on theoretical physics is wasteful when there are pressing practical problems in the world. Why fund research on quantum gravity when people are hungry or sick? This is a fair question, but it's based on a false dichotomy. We can do both. The amount of money spent on fundamental physics research is tiny compared to government budgets. The Large Hadron Collider, one of the most expensive physics experiments ever built, cost about $10 billion over 2 decades. That's less than what's spent on military budgets in a few weeks. We have the resources to explore fundamental questions while also addressing practical problems. Moreover, the skills and technologies developed for fundamental research often have spin-off applications. The World Wide Web was invented at CERN to help physicists share data. GPS was developed for military navigation but depends on understanding relativity. Medical imaging techniques like PET scans use particle physics. The connections between pure research and practical applications are often indirect and unpredictable, but they're real. Investing in understanding the universe pays dividends in unexpected ways. Let's return to the question of emergence. If space-time is emergent, if it arises from something more fundamental, then what does that mean for our everyday experience? We perceive space as continuous. We move smoothly through it. We don't notice any graininess or discreteness. If space-time is made of Planck-scale chunks, why don't we see them? The answer is scale. The Planck length is about 10 to the negative 35 meters. An atom is about 10 to the negative 10 meters. That's 25 orders of magnitude larger. A human is about 1 meter, another 10 orders of magnitude larger. We're so much bigger than the Planck scale that we can't possibly perceive its structure directly. It would be like trying to notice individual atoms by looking at a building. You can't see the atoms. The building looks solid and continuous, but zoom in far enough and you'd see it's made of discrete units. Similarly, space-time looks continuous to us because we're enormous compared to the Planck scale. We average over trillions upon trillions of quantum units of space. What we perceive as smooth motion is actually a quantum process happening at scales so small we can't detect them. This doesn't make our experience illusory. The building is real even though it's made of atoms. Space-time is real even if it's made of quantum loops or strings or bits of information. But it does mean that space-time is not fundamental in the way we might have thought. It's an effective description, a useful approximation that works at the scales we can access. At the deepest level, reality might be very different from what we perceive. This is a common theme in physics. Our intuitions, shaped by everyday experience, often mislead us about the fundamental nature of things. Matter seems solid, but it's mostly empty space. Objects seem continuous, but they're made of discrete atoms. Time seems absolute, but it's relative. Space seems passive, but it's dynamic and curved. Each time physics peels back another layer, we discover that reality is stranger than we imagined, and we're likely not done. Quantum gravity will probably reveal another layer of strangeness. Space-time itself, the arena in which everything happens, might be an emergent phenomenon arising from something even more bizarre. Maybe that something is quantum entanglement. Maybe it's quantum information. Maybe it's something we haven't conceived of yet. There's a philosophical question here about the nature of reality. Is there a final layer, a truly fundamental description beyond which there's nothing more? Or is it turtles all the way down, with each layer emerging from a deeper one without end? Most physicists hope for a final theory, a theory of everything that explains all phenomena in terms of a few fundamental principles. String theory is an attempt at such a theory. It aims to describe all forces and particles in terms of vibrating strings in higher dimensional space. But maybe the universe is more subtle. Maybe there's no final theory because the concept of fundamental doesn't apply. Maybe each level of description is useful in its own domain, but none is more real than any other. Atoms are a useful description for chemistry. Molecules are useful for biology. Cells are useful for physiology. Organisms are useful for ecology. None of these levels reduces completely to the one below. Each has emergent properties that aren't easily predicted from the lower level. Maybe space-time is similar. It's a useful description at large scales. Quantum fields are useful at smaller scales. Strings or loops or information might be useful at even smaller scales. But none of these is the true reality. Reality is the whole tower of emergent descriptions, each valid in its own domain. This is a minority view among physicists, most of whom believe in reductionism, the idea that higher-level phenomena can in principle be explained in terms of lower-level ones. But it's worth considering. Let's think about time again. We've talked about space-time, but time deserves special attention. Time is peculiar. It has an arrow. It flows from past to future. We remember the past but not the future. We can influence the future but not the past. These asymmetries are part of our deepest intuitions about how the world works. But they're not in the fundamental laws of physics. If you film a planet orbiting a star and play the video backward, it still looks like valid physics. The equations work the same way. If you film a collision between particles and reverse it, it's still a valid collision. At the microscopic level, time symmetry holds. The laws don't distinguish past from future. The arrow of time emerges at macroscopic scales due to entropy and the second law of thermodynamics. But why? Why did the universe start in a low entropy state? If we understood the Big Bang, if we knew what happened at the beginning, we might understand why time has an arrow. Some physicists think time might not be fundamental. Carlo Rovelli has argued that time is an emergent concept that arises when you average over quantum states. At the fundamental level, there might be no time. There's just a quantum state, a mathematical object that encodes all possible configurations. Time emerges when you look at macroscopic variables, when you coarse-grain and ignore details. What we call the flow of time is really the evolution of these macroscopic variables toward equilibrium. If this is correct, then time is like temperature. Temperature isn't fundamental. It's an average over the kinetic energy of molecules. If you track every molecule individually, there's no temperature. Temperature emerges when you look at statistical averages. Similarly, time might emerge when you look at statistical averages of quantum states. At the fundamental level, there's no time. There's no before or after. There's just the quantum state. This is hard to accept because we experience time so directly. Our consciousness seems to flow through time. We experience moments in sequence. We make decisions based on memories of the past and expectations of the future. If time is emergent, what does that say about our experience? Is consciousness also emergent? Does it depend on macroscopic averages? These questions take us to the boundary between physics and philosophy, between science and metaphysics. Physics can tell us how things behave, but it struggles with questions about what things are or why they exist. Why does the universe exist at all? Why these laws and not others? Why is there something rather than nothing? These might be questions that physics can never answer, or they might require a shift in perspective, a new framework that encompasses both physics and something else. Some physicists think the answer to why these laws is the anthropic principle. The laws are what they are because if they were different, we wouldn't exist to ask the question. In a multiverse with different laws in different regions, we find ourselves in a region where the laws permit life. This is not a very satisfying answer for many people. It feels like giving up on finding a deeper explanation. But it might be correct. Maybe there is no deeper explanation. Maybe the laws are arbitrary, a cosmic accident, and we exist by chance in a region where conditions are right. Others think there might be a unique theory, a mathematical structure so constrained that it couldn't be any other way. String theorists hope that string theory is such a structure that once you specify a few initial conditions, everything else follows inevitably. The number of dimensions, the particles, the forces, the values of constants, all determined by mathematical consistency. If this is true, then the universe is the way it is because that's the only mathematically consistent way it could be. We don't know which view is correct. We don't even know if these are the right questions to ask. Physics has always surprised us. Every time we think we're close to the final answer, we discover something new that opens up more questions. When Newton formulated his laws, some people thought physics was essentially complete. Then we discovered electromagnetism, relativity, quantum mechanics. When quantum mechanics and relativity were established, some people again thought we were close to a final theory. Then we discovered dark matter, dark energy, accelerating expansion. The universe keeps surprising us. Maybe quantum gravity will be the final piece. Maybe once we understand space-time at the deepest level, everything will click into place and we'll have a complete picture. Or maybe quantum gravity will open up new mysteries we can't imagine yet. Maybe we'll discover that space-time emerges from something even stranger, and we'll need to understand that. Science is an endless process of discovery, each answer leading to new questions. But that's not a reason for pessimism. It's a reason for excitement. We're part of a grand adventure, a journey of understanding that spans generations. We build on the work of those who came before us, and future generations will build on our work. Einstein built on Newton. Hawking built on Einstein. Someone will build on Hawking. Each generation pushes the boundary of knowledge a little further, and we're living at a special time. We're the first generation with tools powerful enough to seriously probe quantum gravity. We have gravitational wave detectors. We have telescopes that can photograph black holes. We have experiments searching for dark matter and measuring the cosmic microwave background with incredible precision. We have supercomputers that can simulate the universe. We have mathematical frameworks like string theory and loop quantum gravity that might describe quantum space-time. We might not solve the mystery in our lifetimes, but we're part of the process. Every observation, every calculation, every idea contributes to the eventual understanding. Even failed ideas are valuable. They tell us what doesn't work, narrowing the search space. Einstein spent decades trying to find a unified theory and failed, but his attempts taught physicists valuable lessons about what to look for and what to avoid. So where does this leave us? We use space-time every day. We navigate using GPS. We predict eclipses. We detect gravitational waves. We photograph black holes. Space-time is as real as anything in physics. But we don't know what it is. We don't know if it's fundamental or emergent. We don't know if it's continuous or discrete. We don't know what happens at the Planck scale. We don't know what replaces the singularities in Einstein's equations. These are not small questions. They're some of the deepest questions in all of science, and they're hard. They require combining quantum mechanics and general relativity, two theories that seem incompatible. They require understanding physics at energy scales we can't reach with experiments. They require mathematical tools we're still developing. They require insights we haven't had yet, but the questions are worth pursuing. Understanding space-time means understanding the stage on which everything happens. It means understanding gravity, the force that shapes the cosmos. It means understanding black holes, the most extreme objects in the universe. It means understanding the Big Bang, the beginning of everything. It means understanding whether there are other universes, whether time travel is possible, whether wormholes exist. And beyond the practical questions, there's the sheer wonder of it. Space-time is the fabric of reality. It's what the universe is made of. Understanding it means understanding existence itself at the deepest level. That's worth pursuing for its own sake, regardless of applications. Humans are creatures who ask why. We want to know how things work. We want to understand the universe we find ourselves in. Einstein gave us the idea of space-time over a century ago. It was revolutionary. It changed how we think about gravity, motion, the cosmos. It predicted black holes and gravitational waves and the expansion of the universe. It's been tested thousands of times and has never failed. It's one of the most successful theories in the history of science. But Einstein would be the first to tell you it's not complete. He spent the last decades of his life trying to go beyond it, trying to unify gravity with quantum mechanics. He didn't succeed. Neither has anyone since. The problem remains open. What is space-time? The question Einstein asked is the question we're still asking. And somewhere, someone will find the answer. It might be a physicist working today. It might be someone not yet born. It might come from a sudden insight or from decades of grinding work. But it will come. Every great question in physics has eventually been answered. The nature of light, the structure of atoms, the origin of species, the age of the Earth. Questions that once seemed impossibly hard are now understood. The mystery of space-time will be solved. When it is, it will be a triumph of human intellect, a testament to our ability to understand the universe through observation, mathematics, and reason. It will open doors we can't imagine. It will change how we think about reality, and it will surely raise new questions we haven't thought to ask. Until then, we live with the mystery. We use Einstein's equations to describe the universe. We calculate orbits and gravitational waves. We design satellites and predict eclipses. We photograph black holes and detect ripples in space-time. The mathematics works. The predictions match observations. But underneath it all, there's something we don't understand. Something fundamental about the nature of space and time that eludes us. This situation is actually common in physics. We often use theories that work perfectly well in their domain, even though we don't fully understand what they mean. Quantum mechanics is the most precisely tested theory in history, yet physicists still debate what the wave function is and what happens during measurement. We use quantum mechanics to design computer chips and lasers, but we don't all agree on its interpretation. The same is true for space-time. We can use general relativity without fully understanding what space-time is at the deepest level, but there's a difference. With quantum mechanics, we have a complete mathematical framework. We know how to calculate anything in principle, even if the calculations are sometimes too complicated to carry out. With quantum gravity, we don't have that. We don't have a complete theory. We have pieces, hints, different approaches that might be pointing toward the answer, but we don't have the final framework. This is frustrating, but also exhilarating. We're standing at the edge of knowledge, looking out into the unknown. Every physicist working on these problems knows they might be the one to make the breakthrough. Every graduate student studying quantum gravity knows they're working on one of the deepest unsolved mysteries in science. That's exciting. That's what draws people to this field. Think about what we've learned in the past century. In 1920, we didn't know the universe was expanding. We thought the Milky Way was the entire universe. We didn't know about other galaxies. We didn't know about the Big Bang or dark energy or black holes. We didn't have quantum mechanics or general relativity. The entire modern understanding of cosmology and fundamental physics has been built in the last 100 years. In 1920, no one could have predicted what we know now. If you told someone in 1920 that the universe is expanding, that it started in a Big Bang 13.8 billion years ago, that space itself is curved by mass, that there are objects so dense that light can't escape them, that we would detect ripples in space-time. From black holes colliding billions of light years away, they would have thought you were insane. And yet all of this is now established fact, confirmed by countless observations. So what will we know in another 100 years? What discoveries await that we can't imagine today? We'll surely understand quantum gravity by then. We'll know what space-time is made of. We'll know whether string theory or loop quantum gravity or some other approach is correct. We'll know whether the Big Bang was truly the beginning, or whether something came before. We'll know the fate of the universe, whether it will expand forever or collapse or undergo some transformation we can't predict. We might know whether other universes exist. We might have detected signals from them or found indirect evidence in the cosmic microwave background. We might understand the nature of dark matter and dark energy. We might have unified all the forces of nature into a single framework. We might have built quantum computers powerful enough to simulate quantum gravity. We might have detected quantum gravitational effects in precision experiments. Or maybe we'll have discovered something completely unexpected. Maybe there's a layer of reality below quantum gravity that we haven't imagined. Maybe space-time emerges from something that's not even in space or time. Maybe consciousness is connected to quantum gravity in ways we don't understand. Maybe the universe is fundamentally mathematical or informational or something else entirely. Science has a way of surprising us. The answer is often something no one predicted. But whatever we discover, it will be discovered by people like us, humans with curiosity and persistence and creativity. People who look at the universe and ask questions. People who do the hard work of developing mathematical frameworks and analysing data and testing ideas. People who accept that most ideas will be wrong but keep trying anyway. That's how science works. That's how we've come to understand as much as we do. And the journey is worth it even if we never reach the final answer. Every step forward is valuable. Every observation teaches us something. Every failed theory narrows the search space. Einstein's theory of gravity is beautiful and profound, even though it's not the final answer. Newton's laws are beautiful, even though they're approximations. Understanding emerges gradually, each generation building on the last. We're part of that process. We're living through a time when the mystery of space-time is still unsolved. Future generations will look back at this era the way we look back at the pre-relativity era. They'll read about how physicists struggled to understand quantum gravity, how they proposed different theories and searched for experimental evidence. They'll see our time as the transition period between Einstein's classical space-time and whatever comes next. And they'll remember the people who contributed, not just the famous names like Einstein and Hawking, but also the thousands of researchers who worked on the problem, the experimentalists who built better detectors, the theorists who developed new mathematical tools, the graduate students who did calculations and wrote papers, the teachers who explained these ideas to new generations. All of these people are part of the story of how humanity came to understand space-time. So when you think about space-time, when you use GPS or read about gravitational waves or look at pictures of black holes, remember that you're seeing one of the deepest mysteries in science. You're seeing evidence of something real, something physical, something that exists and affects the universe in profound ways. But you're also seeing something we don't fully understand, something that hints at deeper layers of reality we're still trying to uncover. Space-time is real. We can measure it. We can detect its curvature. We can photograph it bending around black holes. We can feel its effects in gravitational time dilation. Your GPS works because engineers understand how to correct for the curvature of space-time. Gravitational wave detectors work because physicists understand how ripples in space-time affect laser beams. All of this is real and practical and tested. But what is it? What is space-time made of? Is it fundamental or emergent? Continuous or discrete? How does it behave at the Planck scale? What replaces singularities? These questions remain open. They're some of the deepest questions in physics. And answering them will require new ideas, new mathematics, new experiments. It will require the next Einstein, the next generation of brilliant physicists who can see what we're missing. Maybe that person is working on the problem right now. Maybe they're a graduate student at a university, staying up late working through equations, trying different approaches, slowly piecing together the answer. Maybe they're a professor at a research institute, collaborating with colleagues around the world, building on decades of previous work. Maybe they haven't even started their career yet. Maybe they're in high school, fascinated by physics, dreaming of solving the great mysteries. Whoever they are, wherever they are, they're standing on the shoulders of giants. They're building on Einstein's insights about the equivalence principle and curved space-time. They're building on Hawking's work on black hole thermodynamics and quantum radiation. They're building on the development of string theory and loop quantum gravity, and the holographic principle. They're building on the observations of gravitational waves and black hole shadows, and the cosmic microwave background. And when they make the breakthrough, when they finally understand what space-time is, it will be a moment of profound beauty. It will be one of those rare moments in human history when we suddenly see deeper into the nature of reality. Like when Newton realized gravity follows an inverse square law. Like when Einstein realized space and time are relative. Like when Hubble realized the universe is expanding. like when Watson and Crick realised DNA is a double helix. These moments of insight change everything. The breakthrough in quantum gravity will be like that. It will change how we think about the universe. It will open up new areas of research. It will lead to technologies we can't imagine. It will inspire a new generation of physicists, and it will answer some of the deepest questions humans have ever asked. What is the universe made of? How did it begin? What is the nature of space and time? But until that moment comes, we live with the mystery. And that's okay. That's part of the adventure. Science isn't just about the answers. It's about the journey. It's about pushing the boundaries of what's known. It's about asking questions that seem impossible to answer and then figuring out how to answer them. It's about the excitement of discovery, the frustration of being wrong, the satisfaction of getting one step closer to the truth. Spacetime is Einstein's idea, an idea that revolutionized physics, that explained gravity as geometry, that predicted phenomena we've now observed. An idea that's been tested countless times and has never failed. An idea that works beautifully in its domain. But it's not the final answer. It's a waypoint on the journey toward deeper understanding. And that deeper understanding is waiting for us. Somewhere in the mathematics, somewhere in the patterns of gravitational waves, somewhere in the quantum states of entangled particles, somewhere in the cosmic microwave background, the answer is hiding. The nature of space-time, the structure of reality at the Planck scale, the quantum theory of gravity, it's there. We just have to find it. Maybe we'll find it through clever experiments. Maybe through mathematical breakthroughs. Maybe through computational simulations. Maybe through a sudden flash of insight that connects ideas in a new way. However it happens, it will be one of the great achievements of human civilization. It will be proof that we can understand the universe through reason and observation, that we can answer questions that once seemed beyond reach. And when future generations look back, they'll remember this era. They'll remember when humans knew that space-time exists but didn't know what it is, when we could measure its curvature but couldn't explain its origin, when we could detect its ripples but couldn't describe its quantum nature. They'll remember this as the time before we understood, the time when the mystery was still unsolved. But they'll also see it as the time when we laid the groundwork, when we developed the mathematical tools, when we built the detectors, when we made the observations that would eventually lead to the answer. Every era contributes to the next. Every question answered makes the next question clearer. Every mystery solved reveals a deeper mystery. That's the nature of science. That's the nature of human understanding. So here we are, living in a universe we don't fully understand, using theories that work but that we know are incomplete, asking questions about the nature of reality that we can't yet answer, standing at the edge of knowledge, looking out into the unknown. Space-time surrounds us. We move through it. We measure it. We observe its effects. But we don't know what it is. And that's beautiful. That's what makes this exciting. We know enough to ask good questions. We know enough to see the puzzle. We know enough to work toward the answer. But we don't have the answer yet. We're still searching, still exploring, still trying to understand the universe at its deepest level. That's the state of physics today. That's where we are with space-time. We've learned so much. We've come so far from Newton's absolute space and time. We've detected gravitational waves. We've photographed black holes. We've measured the expansion of the universe. We've pushed our understanding to the edge of what's possible with current technology. But the biggest questions remain. What is space-time? Is it fundamental? What is it made of? How does it behave at the quantum level? These questions will define the next era of physics. These questions will drive research for decades or centuries. These questions will eventually be answered, and when they are, everything will change. Until then, we keep working, we keep observing, we keep calculating, we keep thinking, we keep pushing the boundaries. Because that's what humans do. We ask questions, we seek understanding, We want to know how the universe works and what it's made of and why it exists. These drives are fundamental to who we are. They define us as a species. So the next time you look up at the night sky, remember this. You're looking at space-time. The stars are separated by vast distances in curved space-time. Their light has travelled through space-time for years or centuries or millennia to reach your eyes. The gravity you feel is the curvature of space-time beneath your feet. The passage of time you experience is the flow through the time dimension of space-time. Everything you see, everything you experience happens in space-time, and we don't know what it is. We use it, we measure it, we describe it mathematically, but we don't know what it fundamentally is. That's the mystery. That's the frontier. That's where physics is heading. And somewhere, somehow, we'll find the answer. We'll understand space-time at the deepest level. We'll know what reality is made of. That day is coming. It might be soon, it might be far in the future, but it's coming. And when it arrives, it will be one of the greatest moments in human history. The moment when we finally understood space-time. The moment when Einstein's idea was completed. The moment when the mystery was solved. Thank you for joining me on this journey through space-time and its mysteries. If you found this exploration valuable, a like or subscribe would mean a lot. It helps me continue making these deep dives into the cosmos. And remember, the universe is full of mysteries waiting to be solved. Space-time is just one of them, but it might be the most important one. Good night.